Okay, we are live. Just gonna wait a little bit to. I will just share the stream on Instagram. So there are some viewers. Let's see. I have to make it public though. Right. Yeah. Oops. Now we're public. Let's just share this. Okay, let's I will okay, shared it. I just need to see if the audio is good enough, and if there's some problems with the audio, please let me know. Okay, I think there are no problems with the audio. I just want to share the stream as well too. So can I just this. Okay. Just do this. All right, we should be live. All right, so today we are going to talk about different kinds of, so we're going to try to come to we're going to try to learn about different fields. So what are fields? What are some things in this theoretical spectrum of mathematics that can help us solve some problems? Also, I want to start off with like easier problems to just get the greetings to you, David. I hope you have a nice day, and I hope we learn some things together. Just gonna start out with some easier problems, and then we're going to go into more and more tougher problems. And at the end probably see some like FFT or something like that, and I will show you a cool FFT problem, and why FFT actually matters in competitive programming. So okay, I have two screens here. I will just jump in here when I want to show you to show you like some things. I was just looking at some empty completeness, but that's for a totally different stream. Okay, so on AtCoder, so there is this site Kenku or whatever that pronounced, and you can see what problems you have solved and what you have tried to solve and got the wrong answer to. But I found here one very interesting problem, maybe to start the day off. Okay, I have lost the stream. How did I lose the stream? What is going on here? How is the stream? Can anyone tell me in the comments how is the stream? Because I have lost stream health is good. So apparently now stream health is good. If there are some hiccups in the stream, please tell me in the chat, because I see here the stream health, but I may just forgot to check it. Okay, so I found this kind of cool problem. It doesn't have a lot of difficulty. It's just 2,700 somehow. And I want to solve this solve this problem. This is going to be our first like introductory problems to some like XOR mathematics. It's definitely a very hard problem. It has rated being one of the it's the hardest problem on this contest, right? But we are going to try to solve it. So you're given a sequence of n positive integers. Process q queries. In the ith query, determine whether it is possible to choose one or more elements from some subset, from some subsegment of the array, so that their XOR is equal to some given element. So what does that mean? I will just check one more on this one more time about the stream. Is it good? Is it? I'm not sure what is going on with the stream. Is it good enough? I think it's good enough, right? But yeah. So okay. Nice. So let's go back to the problem. So the problem is okay. I should shut down some things that I need. Okay. So the problem asks you about some subsegment, and if you can pick some numbers in this subsegment such that their XOR is some given number, and the numbers are very high, very big, and the subsegments can be enormous as well, right? So there are a lot of elements here. But we talked about something on a previous stream of mine, and this was about the Gaussian elimination in base 2. So the Gaussian elimination in base 2, if you want to solve this problem and you're watching the stream after it happened. So probably this stream will be just public to watch it after it happened. But if you're solving this problem, I would suggest right now just thinking about how would you implement this and stuff like that, and then maybe continue the video. But for now, I'm just gonna go and try to solve this problem, right? So you have these one or more elements. You have this subsegment, and you need to say if this subsegment, if with some elements you can create this element, XORing them. So I've talked about the Gaussian elimination in base 2, and Gaussian elimination in base 2 exactly tells you, given some set of elements, if when you do Gaussian elimination on all of them, on all of these vectors, you will find out you will have linearly independent vectors. So if I draw something, it would be a much nicer way to show you what actually I mean about Gaussian elimination in base 2. And we're gonna just go solve the problem and go further, because this problem shouldn't take a lot of time. So let's say you have some. Okay, let's just change the color. Maybe this is a better color. So you have some vector. So this here is one number in binary, right? But you can imagine it as a 9-dimensional vector. So in our case, this is a 9-dimensional vector. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And each bit represents this this dimension is the vector does this vector in this dimension have some power, right? And now you take another vector and you say, okay, let's say that this is this vector, and if you XOR these two vectors, the XOR of these two vectors will, so the XOR is just simply this, this. So now you're getting you get a smaller. I mean, it doesn't need to be a smaller. Right? You're getting another vector, right? It's the same 9-dimensional vector. If you do this, it's the same 9-dimensional vector, right? But we just don't write it like that, okay? And now when you have this vector, so it means the dependency between these two vectors can be written as this vector. So if I have this vector and this vector, I can get the other vector, and vice versa. So if I have this vector and this vector, I can get this vector, because of the XOR commutative property, and this tells us the dependency, the dependency between these two vectors. So if I have all of these three vectors here in some set, right? What I only need to remember is I need to remember this vector and this vector, and we can prove that if I have this here bit on, right? I don't want to remember this vector here, because this bit here is on. It doesn't make sense to remember this vector, but it makes sense to remember this vector, because the furthest left bit here is actually here. And what this tells us, that in this dimension we already have this bit. So XOR 0, we can create this. We can create any vector here starting with 1, because we have, let's say we have these two vectors, right? So let's have these two vectors, right? So we can create any vector that starts with 1, because we can XOR these two, and we can create one here, right? But it's not actually any vector, because we don't have more vectors. But what this vector here will have somewhere this L position, this left position will be somewhere not here. So here, 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 or whatever. And this actually allows us to create a to make a Gaussian elimination in base 2. Actually, this is a quite fast procedure. XOR is one of the fastest operation, if not the fastest operation in the computer, right? So you can create this Gaussian elimination on huge bit sets very, very quickly. And okay, so we have these two vectors, right? And these two vectors can get this vector here. So even though we don't have that vector, but we can create it by joining these two vectors. And now imagine that you have like 9 bits, right? Here's a question to the audience, if the audience actually listens. So how many vectors do I need if I have 9 bits, right? Which is a little bit off, but like let's just consider we have 9 bits, right? We have 9 dimensions. Okay, so how many vectors do I need to create any number? So like let's say I'm given some number, and I say, okay, I need to create this number by XORing some vectors, but how many vectors? Hello Blagoy, what's up today? We're going to talk about Gaussian elimination in base 2. We are talking about now in Gaussian elimination in base 2. We are going to solve one segment tree problem. Maybe for some audience members this is a little bit off the rails. Like the difficulty of this stream maybe will be very high, but I'm trying to start with like easier things to explain, and then go, and you can rewatch this stream. So like I will have this public, so like if you haven't heard, like if you weren't here, I will just put it public so you can rewatch some things, but yeah, we just started, so like you haven't missed anything. Okay, so I was talking about this. So like given this number, so like I have this number in like, let's say this number is A, it doesn't matter. Okay, let's say this number is A. Let me just what I will do here, because it's maybe better just to do this, because you can't see the whole monitor. I will just put it like this, so I know I have only this room here. So you're given this number, let's say some number, right? You can write it in binary and okay. But now I'm asking you, if I have how many vectors do I need to create this number with XOR, such that each vector, if I have them of this type, so this number is 9-dimensional. Actually, they should be this. So like I have, I'm going to say that this number is 9-dimensional vector. What this means, that I have 9 bits here. So here I have 9 bits, right? So okay. Now if I'm giving you these vectors, which are all 9-dimensional vectors, like okay, these are going to be is this 9-dimensional? Yeah, this is 9-dimensional. Then I will have like this vector, then I will have this vector, and so on. So like you get the point. So like you have ones in every of these, right? So if you have all of these vectors, if you have all of these vectors, you can pick exactly what vectors you need in order to create this vector here. So if you have all of these vectors, which we say in theoretical mathematics, we say that these vectors, these numbers, but I'm just saying here vectors, these vectors are all linearly independent. What does linearly independent mean? It means that if you have this system of vectors, and you pick any of these two vectors and you XOR them, it will never be 0 at the end. So if I have, if now here I would take this vector and XOR it with let's say this vector here, it will never be 0. But if I have in the same vector here somewhere below, XORing this vector and this vector will be 0. So if you have sets of two equal vectors, it won't be independent. So why do we need this? Why do we need this? We need this to create such a small set of vectors, such that you can create any possible vector with these, just picking the right ones. So like you only need 9 vectors, and if you only know these 9 vectors, you can create any possible vector with XORing some of them. So if I want to create this A vector here, I can pick this, I can pick this, I can pick this. So like I will pick these vectors. So I will pick this vector, I will pick this vector, I will pick this vector, I will pick this vector and this vector. And when I XOR them, I will get exactly A. So actually to create A, you need less than 9 independent vectors. Okay, you need exactly the many independent vectors, how many bits you have. Now you have like 5 bits on, you need 5 independent vectors. Because in 5 dimensions, this vector has some power. In the other dimensions, this vector doesn't have power. Okay, so let's go back to the problem. So the problem asks us to determine on a given range. So it says, okay, you're given some n integers, right? Given some k queries. The I query is to determine whether it is possible to choose one of or more elements from this range here. So choose some elements such that their XOR is some given I element, some given element. So for each query, you're given the size of the query. So here, the range where you're asking, and you're given what their XOR should be. Okay. So when how do you solve this with the knowledge now that you have, right? With the knowledge now that you have, you can probably, if you want to think about it, and just tell me in the comments if you just want to ponder. But I don't recommend now pondering, because you still don't know what Gaussian elimination does in base 2, or you have maybe seen my live stream and already know what Gaussian elimination does. But okay, so how would we solve this problem? So it is very obvious to see that this is exactly what we need, the Gaussian elimination. So if you have some huge range, you don't need to remember all of them. You just need to remember exactly many vectors as their dimensions. So here, each element goes to 60 dimensions. So 2 to the 60. So this means that each element has 60 dimensions. So each element can be represented as a 60-dimensional vector. And when you know this, when you actually know that this element can be written as 60 dimensions, you only need 60 vectors in each of these spaces. So like in each segment of the segment tree, you only need to store 60 vectors that represent what dimensions you can create. And how do you store this? You just have, for each node in the segment tree, you have some vector that, like, you have some array or a vector that stores these integers. Because like now I'm talking about these integers as vectors. So like it's a little bit maybe confusing for the new but bear with me. Like a vector in linear algebra is exactly a type an array, but now because we have like 60 on and off, we can just represent them as bits. Doesn't need to be a Boolean array, because it's already in bits. It's much easier to work. Or you can do it with bit sets. Let's say, doesn't matter. Bits, vector of booleans or integers, they're three interchangeable things, as long as you know how to manage with them. Okay, so now let's solve this problem. This problem is I will say again the hardest problem on this contest. So it is really like probably, okay, if I say the standings, there's probably, okay, I have participated in this contest, but this was like probably a long time ago. So let's see the official standings. How many solved this problem? Very little. So like the chance of us solving this problem is little as well. But still, I hope that our Gaussian elimination will work. You know, let's see. Maybe we will embarrass ourselves, but maybe we'll solve the problem. So I don't know. Maybe it's time limiting, because there's a lot of queries. So maybe 60 times the probably 3 seconds will be enough. I don't know, let's try. Okay, so I have this CPH judge here, which just copies the problem from the contest, and if I switch over to the other screen, I can see this, right? So I can choose CPP, and now all of the test cases are here. So let's start coding really fast so we can solve this problem quickly and move on, because we're already 25 minutes in the stream, and I'm just explaining Gaussian elimination. Whoa, where's the other? Okay, this is a segment tree that is actually coded with the help of Martin. Martin is doing a workshop in Macedonia in I mean on the 27th. So if you haven't seen that, go. Yeah, this segment tree is very old, so this segment tree allows me to, like, I have added this node here structure, which can save for each node what I want to save and how do I merge two nodes together. And also I have bitwise. Okay, I don't have the struct, but I will get the struct because I want to add more. Just bear with me. I want to make it better. Just bear with me to get the struct. Yeah. Okay. Yeah, so this is the bitwise Gaussian elimination structure. We are going to say that the log now is 61, let's say, and now you need to have this as in the bases we are longs. We're getting longs, and yeah, so like I can insert a vector in this Gaussian elimination by doing this. All right. Also, I want to create such a operator where I can merge them. So if I have two structures, two bitwise Gaussian elimination tables, I can merge them. So I will go for every vector in the bases. Now I don't want to save all of these vectors, but let's see. Maybe it will pass the time limit. I don't know. 60 is not that much to save, but maybe we can optimize it further. Okay, so go basis size. Okay, so how do we merge them? For each of the basis vector, I'm going to say, okay, we create some kind of bitwise here Gaussian function, new table, so result, and then we say result.insert vector of the basis dot size, and the result actually I'm going to copy our basis, so result.basis is our basis. So I'm going to copy our basis, I'm going to insert, not that size, I'm going to insert the vector, and I'm going to return result. And this make a constant operator, and yeah, that's pretty much it. So now I can merge two data structures, two bitwise Gaussian data structures together. Okay, now I will want to, okay, here I will have bitwise Gauss, and I will say like, okay, value or yeah, whatever, doesn't matter. Okay, so each node will have this. But of course now the nodes are too big, so let's say that, okay, the power is now probably too big, right? Or it's not actually. It's not, it's fine. I don't know, let's say it will probably pass. But okay, so when we want to merge them, I'm just gonna merge them like this. And because we already written this operator here, this already works. So this is it, this is all I need to do. And now for the problem itself. So I need to enter all of these into some a vector, let's say this. Also, yeah, okay, this is fine. I mean, we can improve the complexity here somehow. Okay, so okay, I need to read for how many queries do we have, and for each query. So I may like, why not just maybe put somehow. I can't really, the screen is too tight to see the the problem is this, so like I'm just gonna let's see, I'm just gonna put it in chat, so for those who so this is the problem. Okay. So let's try for each query. We have L and R, and we have some integer X. We read them all, and then we say, when we read them all, we say, okay, we query onto the segment. So I will just say, okay, I will get the bitwise Gaussian function from some tree. Okay, let's just tree here. Yeah, okay, so tree.askLR, and I will ask for L-1R. So from this segment, this is essentially saying this. Okay, I will ask them, and now because I want to optimize this as much as possible, I'm just gonna add this this thing so it's faster. But okay, I can't add it right now. I'll add it after, before submitting. Okay, so I will ask this about the value, and now the value is actually the bitwise or the bitwise Gaussian, right? So excuse me, what? Oh, because it's constant, it's I mean, is it constant? I don't want to copy this. I want to get a reference to, right? Can I get a reference to it like this? Why is it allowing me to get a reference to? Okay, doesn't matter. I'll try fixing it. And I will say, okay, okay, I have this, and I want to make another function here, where it says like, can I create this vector, right? And oh, I need to change this SLL, so LL. So can I create this vector? And okay, so what we said, if we can create this vector, I will go through all of these vectors, and I will say x is XORing with I will say, okay, x is XORing with basis at I. I'm just thinking if I need to skip this. I don't think I need to skip this. And then I will return if x is not if x is 0. So if x is 0 at the end, then I can create this vector. I think so. Now g.can x is what I will want to print out. So like I want to print out yes if it can, and no if it can't. And now I want to put these in the segment tree. So there are no updates, so I can't do this without a segment tree. I can do some decomposition, but a segment tree is better. I think so. So I can put every. I don't want to. Okay, whatever. Let's try this. I need to create a function where where I can build the segment tree off of some given array. That's a must that I can do. Shall we do it? Like, need like a function that will build the segment tree off of some given array. So like given some essentially vector of nodes. I need to have here vector of nodes, and then here I need to have, okay, the index is actually v at index, no? and then I will just build them recursively. Okay, this should work. Oh, it's not actually v at index. No. It's wait, is it? No, it's not. Okay, I merged these two, but v is okay. I go here. At left? Can we do at left? I think I can do it left, right? I think, but what I'm going to do is I'm not going to build the tree in this way. I'm going to first build the tree like, I'm just going to do like, whatever, because I don't know what is this node defined as. I need to define it here. Okay, let's define it like this. And now for each of these, I will say, okay, I create some node and new node, whatever, new node dot value dot basis at 0 is a of I, and I say tree put at I this new node, and this should work. If I haven't missed anything. Okay, it's okay, to create this tree is a little bit slow, which is fine. But why it is not? This can returns is it XORing all? Yeah. I mean, no, I don't want to XOR all of them, right? Do I want to XOR all of them? Now I have some vectors, and then I want to check. Okay, so if x is 0 at any case, I'll just return true and return false here. Is that the solution? Okay, it passes the samples, which means that that's the solution. But one more thing, I need to optimize this because this, I think it's too slow. I think it's too slow because I'm adding all of these nodes. So can I say, okay, like this? So can I create a vector of nodes here, and can I say, okay, I'm just gonna create these nodes. Let's say this is int x, c in x. I create a new node. I add to the basis. Actually, I want to insert this vector now. Insert vector. So let's just do this because I don't know if. I mean, it should work. It should work because we never do it. But let's just be safe. Let's just do insert vector a of I. Has, oh, not on the basis, I want on the node. And yes, okay, that's correct. Okay, that is correct. Now, let's submit this just to see that actually this is too slow. I would think it is too slow. Let's just submit and see if it is too slow. I will just untie this so it's faster. Maybe it is fast enough, but I don't think so. Yeah, I think you should time limit because the tree is just too big. Okay, so it times limit. Okay, so I need to optimize this, no? Let's where should we go? Here? No, not here. Let's go back to the problem. Okay, it doesn't matter. Just go here and let's optimize this. Okay, let's see that if this node is created here. So this is some node, and we create this node. Like 60 shouldn't be that much. I think it should be fast enough. Huh? Maybe I'm wrong. Can you know this? So like I'll say a and I and I dot value. Insert this vector. No. We insert this vector, and now we have tree dot build, and we say okay a, right? We build the tree with a, and if everything works to plan, I should have a tree built. All right. Okay, it's stealing, but I mean, all of the test cases, is that slow? Now it should be faster. Now it should be faster. It's just that like on each query, you have 60 times 60, so like it's a big constant factor though. Yeah. This is a big constant factor here. So how do you optimize this? How do you optimize this factor? You don't insert a vector if it is 0. So like one thing I can do is like if g of basis at I is 0, I can just skip it. And I know that if it is 0, actually I can break. Oh, I can't? I need to just skip. Yeah, there could be other vectors. Okay, yeah. There could be other solutions. Yeah. But this basis doesn't, I don't need to save all of the bases. I only need to save like some. But still, it's still a huge factor. And also this tree, is it that big? Yeah, it's probably right. Can we do prefix basing? Probably not, right? If I have like one Gaussian to here and the other Gaussian to here, I cannot do that. Yeah, it's stealing all of them. Let's just take a look at how bad is it. Oh, they are so powerful tests, and the memory is half a gigabyte or something. It's all TLEs. Wow. Wait, that's okay. Maybe the approach is not actually that great. This node is too heavy. It's too heavy. It's 60 integers inside. But still, I don't need 60 integers, you know, like. But if I don't need 60 integers, then I need to. I'm not sure. Like it should be correct. Okay, there are a lot. Can I just try submitting it now with like the build step instead of and trying if that would pass? No, it's still time limit. Oh, okay. What can I optimize else? Oh, it's still gonna time limit. If I don't have these vectors, I can't just do. So like the memory has to be that big, right? So let's just take a look at like how fast are these submissions. Let's say this H submission, right? How fast is it? Okay, so it uses a lot of memory, but no, this is not it. This is the submission. So it's quite fast. So it probably doesn't use sec tree, right? Probably. If it is that fast. Because if I need to merge these two nodes, I mean, prefix Gaussian, is it even possible though? Is it even possible, prefix Gaussian? How would that work though? I have some set which is linearly independent but it's bigger, and then I have some set which is linearly independent but it's smaller, and I can't do Gaussian on these two. Square root decomposition? Actually, square root decomposition will be... no, it won't be faster, right? If the query... yeah, it won't be faster because we can't delete from the left side. So like you can't just delete. I was thinking on the most algorithm. Okay, I'm not sure now. I'm just gonna leave this problem as it is. It gets wrong answer on one. So the build doesn't probably it's not correct, but it should be. It gets wrong answer. I just want to see. Or maybe the memory is not that big. It's quite a big structure, the bitwise Gaussian. It's quite a big structure. Okay, I'm just gonna leave this. This is an interesting problem. I'm just gonna leave it like that, and then I will say I told you the probability of solving, but I'll just leave it like this to go and explain something about Nimber fields, what this stream is all about. I mean, it's all about. It's not all about. It's just like an upgrade. Like, I mean, it's should be. Let's see. Well, this is even bigger memory now. How is it so huge memory though? Is it that huge? Yeah, like there could be a lot of optimizations here. I mean, yeah, it should be bigger because we're storing the array. So we're storing the array of Gaussian in this, and then we're accessing memory through that. So yeah, it should be bigger. It should be bigger. But wrong answer here is surprising. Here this is surprising. But okay, until we fix this. Until we fix the time limit, we cannot do it because we're now storing here AIs, so it's a little bit awkward. It's here we're inserting this vector, but this vector is like when it is being inserted here. So like let's just switch to the other screen. So here when it is inserted, if it's 0, and then if the base is not so if it is 0, then we put it. If it is not, we say that okay, we XOR that, and then you go further, and then you go further. So I don't know how to optimize. I mean, I can optimize this in log, but still the memory is huge. This is probably not the way to do it because it copies the structures. What is probably the way to do it is just get all of the Gauss. Yeah, because we're merging like 60, and that's like 60 times log of that. And instead of what we can do is just get the bases, all of the vectors. So that's 60 times log, and then merge them with like some Q's. I'm not sure. Or do dynamically ask about X. Not sure. Okay, we're just gonna leave this problem as it is. We're going to skip it. I had some ideas like introducing like min, cost, max flow problems to the stream, but that's for like another time. I had one interesting problem in mind I wanted to check out. Okay, so we saw how bad actually the bitwise Gaussian elimination is, but still, it's a nice trick to know up your sleeve. Okay, so let's switch to the Nimber field. So I'm just gonna explain quickly what. Okay, instead of explaining, I'm just gonna go to Wikipedia and I'm just gonna like field in mathematics. So I'm just gonna here go and show you some things. Okay, so like this, probably you read. Okay, so a field, yeah, here is like formally defined, right? So a field is a set together with two binary operation, addition and multiplication, and for which I can, so like you can have this mapping inside of the field. So like every the binary operation on two numbers in that field, or two, I'm not sure how they're called. Are they called? I'm not really sure how they're called because there are different interpretations. But I will say just this, like, okay, a mapping on two elements of the field is still inside the field, and there are some properties that have to be satisfied. Associativity, commutativity, identity, so additive and multiplicative identity. So this has to be satisfied. If you add 0 to any of that, or any element, it's still 0, and if you multiply, like it doesn't have to be 0. It just has to be an element inside the field. So, but it still has to satisfy a property. So an interesting problem which I came across is this here, the XOR sum of arrays, which is still a really difficult problem, which I can, if I didn't know, like I still haven't solved it, but I know the solution now, and so it's impractical to kind of go and solve it. But okay, what it asks us about so given some array, just gonna do this. So you're given some array of integers, and you have a specific query you have. So like the query is, so first we may define just operation. So like XOR sum of two arrays B and C is defined as the component-wise XOR, as an array of component-wise XORs. So if I have, like, if B is 1, 3, 7 and C is 5, 3 and whatever, like 8 here. So the bitwise OR of the bitwise the XOR sum of these two arrays is some array S of B and C, where we can XOR these two. So that would be 4, that would be 0, that would be 15. Yeah, right. Yeah. So, okay. So this is defined as SBC, right? So now let's go back to the array. You're given some sequence of non-negative integers, and each query gives you 6 integers for which some conditions satisfy that the difference between A and B is equal to the difference between C and D. And you want to answer this query of, like, is the XOR sum of this array. So let's say this is the array here from A to B, and from, let's say this is the array from C to D. So is this XOR sum strictly lexicographically smaller than some other array? So let's say this array here, E to F, some other sub array, right? So you want, essentially, you have this element XOR this element, this element XOR this element, this element XOR this element, this element XOR this element. So you have like, okay, you have this ACD, no, is this, then you have AB is something else. You XOR all of the components between them and you get some other F, let's say array, right? And then when you get this array, you need to check if it's lexicographically smaller than this. So, okay, so I had no clue how to do this problem. So when you see this here interpretation of lexicographically small substring is lexicographically smaller than another substring, you always have to think about hashing. So that came to mind. Like how we can hash it so that that we can answer these queries in OAuth1 or OAuth log n or something like that, because lexicographically small, if you want to find lexicographically small, you need again to binary search against hashes, but we're not going to go there. I just want to explain a little bit about the solution, about Nimber fields, and I want to learn about other fields that exist. Okay, so essentially you want to, so what they say is you want to do the solution. It involves again hashing. What it came to mind, I just had no idea how to do it with XORs, right? If the problem was the addition bit, if the problem wasn't the XOR here between bitwise elements, if it was addition between them, it would be a straightforward polynomial hashing. But now XOR, I had no clue. So as always, let's read the tutorial, right? And okay, rolling hashes. Now that they say rolling hashes, it's not actually like it. This here is called a polynomial hash, right? It's a polynomial hashing essentially, right? So you're given some like some array, and you some base and some modulo, of course, and you do this hash, right? And you can do this rolling hash technique on these polynomial hashes, right? And then you can do substrings on these polynomial hashes as well. But what is very interesting? Okay, solution when XOR is replaced by the addition, by ordinal addition, right? If the ordinal addition is done, it is very easy to solve. But now, like back to the original problem. Now, instead of ordinal addition between these component-wise, these vectors component-wise, we have XOR, and there they introduce this thing called the Nimber Field, right? And the Nimber Field is essentially a field whose addition is XOR. So like we are interchanging addition, we're changing the addition to XOR, and we're changing the multiplication in this field if the addition is XOR. So like if two elements, we want to add them, it's like XOR. Now the multiplication between the elements is the nim product. And you can quite I mean, how to imagine this? You can imagine this as like, okay, so we know that multiplication of two elements, so A times B, is essentially adding A B times, right? So like adding the element A B times, right? So like if I have A B, so it's easy, right? But now instead of A B, now you have this XOR, right? And get some. And now instead of like A plus B, you have A. Instead of A times B, you have A nim product B. right? Because you're essentially wanting to XOR. So the Nim product is actually defined by this equation here. So I mean, fine. I don't know. I don't know anything. But then polynomial hashes work. So polynomial hashes work, but instead of having the addition, and very commonly here we have this hash technique, right? We pre-compute powers. We pre-compute the powers, right? And pre-computing the powers is essentially in the power Nim product the basis, right? And that's how you get the next power. So x times x is x squared, right? And then when you have x squared, then when you have x squared, then times x is x cubed, and so on and so forth. All right, so they pre-compute the powers in this way, and now when you have like when you shift this polynomial by the basis, you add on this thing the AI. So it's maybe I will make some video about explaining some polynomial hashing, but now for now I just want to focus on like getting this script, this polynomial hashing technique, just to make it get a little bit better, just to have it for like ACM preparations, and then for having for ACM, but also because this is quite cool. Like the Nim product is quite cool. Essentially, it is what it is, right? But maybe first I would like to look at some other interesting fields if they exist. So I don't know how to actually look for such things. If someone knows in the comments, so like, okay, modular fields, yeah. So it's essentially what the Nim product here is calculated. It's calculated module or something, right? It's still, I mean, it's not module. It's I don't know. I have this article here by like the Nim product by some like Japanese dude, which says goes over the Nim product. Let's try maybe to any smaller to okay, and excellent. So he actually like computes this Nim sum with but this is just a technique that is known in probably in Japan only. Like I have never heard this technique before about Nim products. I mean, okay, whatever. Like I don't understand a thing here. So can we somehow translate this? Is it possible? Come on, what? Why? Why can you go up? No, what? So like, why can't I go up? I can't select all. I can't. Wait, can I maybe do this? Yeah. No, so like, if I can do this. Well, let's translate the first 2 pages. Text language. Okay, there's definition. Okay, it says, I don't know what the name product is, but if you just want to solve the problem, it is enough to use what is written in sand. Cats can't read English. But if the expression is it seems that it will be always less than 32, so the rest is the same. It can be obtained recursively. Always less than 32 bits. Like, yeah, that's correct one. Oh, so it will the new product will be always less than 32 bits no matter what you have, and then that is why you don't need to use modulo, because like you are actually using modulo 2 to the 32 essentially, because you're saying always will be less than 32 bits. Okay, this makes sense. This makes all the sense in the world. But why it is always less than 32, that I don't know. Okay, prove that 0 XOR 0 is 0, clearly. Oh, what? Okay. Oh, this is not XOR, this is the sum. The name product. No, not the sum. The sum is actually XOR, whatever. When calculating the name sum, the magnitude relationship is not well. So this expression is commutative and associative. Yeah, that's what we said. Like it is commutative and associative. That's why it is a field. It's a commutative field. That's why it is. Because if it is, but if it weren't, it won't be a field. I used the substitute of induction theorem 4 to establish the equal sign. Okay, doesn't really like. Let's just okay, we translate the first 2 pages. Let's translate the last pages just to go over what weren't these the first 2 pages? Oh no, like yeah, okay. About mean products, the flow proof is roughly the same. I don't know where less you can use these name products other than hashing though. Like, can you come up with a problem that will use the name product? So like the name product without like hashing, except if you do some kind of polynomial thing. So like if you do FFT with the name products, that would be cool. Like do a whole FFT with like name products. Is that even possible? Like the polynomial instead of having like x's? Like no, I don't think that is possible due to the modularity. I don't know. It's complicated, but that would be one place that I would think they could be used. I'm not sure. Also, field of fractions, field constructing fields within a bigger field. Algebraic extension. Okay, there were some techniques that you could exchange like minimum and maximum with some kind of fields. I wanna know some techniques like that. I'm not sure how to find these though. Let's try. So fields, math, topology, minimum, maximum. Yeah, you can't really define minimum due to the fact that it's not like, okay, it has commutative, it has additive, but it does not have the property where, like, okay, minimum. I don't know. Could what kind of property doesn't satisfy this? Like, okay, let's see. Associativity, minimum satisfies. Commutativity satisfies. There exists. Okay, let's say minimum is kind of addition. Okay, let's say the minimum is addition. So if I add 0, so if I minimum 0, it still doesn't do anything. But I can do it as multiplication though. No, I can't do it as multiplication. I can't do it if there isn't a big enough number. So like a minimum. If I say a minimum some big enough number, then it is possible. But this big enough number doesn't have the additive inverses. So like, what would be an additive inverse here? I'm not sure. I'm not sure. But I'm sure that there was a problem with something to do with this. Sequence of steps. Just take a look at the tutorial just to see, like, is it field? Is it fields? I don't know. Alright, maybe min-max properties in topology. So real valid continuous function. Now one can show. Okay, that doesn't make sense. Okay. Field topology. Field topology common field. I'm not sure how to search that, you know. What is this Wikipedia? What? Algebraic topology. Algebraic topology. Fields. It's math fields. Like, yeah, I don't want fields as. I want to see what interesting properties we can come up with. Some like interesting, maybe like multi-dimensional fields somehow. So like, because like complex numbers are fields, then it means that like other quaternions, quaternions are a field, right? It's a field, right? It should be. Still. Okay, I mean, it's interesting. It's interesting. I don't know. I don't know. Optimization on this problem. I don't know. We'll see. So okay, field theory. We can't find something interesting in fields. Let me just check something. So okay, so let's see game theory. I want to learn something. Yeah, so the max function and the grounded numbers. This is very popular. I mean that's essentially the bare bones of game theory. But before beginning with okay, that's no reachable states, grounded theorem. Was if and only if the XOR of the grounded number of the position each sub-game is 0. I mean, preprocessing something with grounded numbers won't be actually that. What the hell? There are problem sets. So okay, this is some course. Okay, in should we do something with grand numbers? No, first I want to do something with name products. So okay, knowing the solution to this problem, like now that we have this solution, let's try to break it down and try to wrap them in some like good enough wrappers. So we have so we have something, right? So let's just name product CPP. Okay, so what do we know? What do we know now here? What do we actually need and what do we not actually need? Actually, the whole solution can be broken down by, okay, here we have some initialization function. Here we have some like name product pre-computation, and we save this name product in a small array. And then when we say, okay, name product, what we want to answer here is to answer this if it's smaller. So wait, what? So like, okay, this is for small name products. It's pre-computed. So for big name products, is gonna be computing it recursively. That's why the name product here is slow, but it's only computed here. when we get, it's only computed once. So technically I actually like this code. It's simple. It's elegant. It can be used like, okay, this, and this. It's all about hashing. Now, what about, like, okay, this is hashing as well. So apparently, just this matrix doesn't fit in here. This matrix doesn't fit in here. So apparently it's like this. U64. So these are here. No, this is the hashing. Hashing portion. So like, okay, I'm not doing bother here. Okay, this is hashing, and with this get function. Okay, I mean send. Can we have you just okay, whatever. Can we just put it in a bool and that's it? But whatever. That's pretty much it. I don't know. I kind of like this code. I kind of like the compactness of the code. It's easy to write, probably. It's very easy to write. Although we need to explain a few things here inside of the code, because I was just forget. So like addition goes into XOR, and multiplication goes into the name product. And okay, so how fast is the name product though? Like should be relative. So should be very fast. Should be very fast. Now I'm thinking about the usage of the name product in other problems other than hashing, but I can't think of anything like right now where could it be used. Like, okay, in game theory, you have the Sprague-Grundy theorem, so you have like already this max calculating, like max function. Where can you other way like use an improd? So where can addition be substituted with x? Like what happens with like with FFT? Let's say you have like some polynomial which is okay. So we know that. Okay, so let's just switch to the other screen. Okay, let's think about this. Let's think about this. So f of x is some, let's say, a of a0, x to the 0 power, and a1 x to the 0, x to the 1 power, and a2 x to the 2 power, and so on and so forth. So essentially this multiplication here is the name product. So like you will have a0 name product x0, and now like the name product is, I think, like this. No, it's like this. And then you have the XOR. So this is XOR, this is name. So this is XOR, and then like XOR and whatever. Okay. But if you have the access as well, so, is it even like, because of the nature of FFT and the way it uses like complex numbers, here there would be like, what would be like e to the I times p omega, like it's what will be I in the Nim product, you know, like in the Nim field, what would be the complex Nim field, you know? That's some interesting theory to think about. So how would you define the complex field, the complex Nim field, the complex Nimber field, or something like that? Can you even define it, if you can? Probably not. I don't know. I don't know. I don't know. I'm not that good in math, so it's interesting to think about. Another way, like the hashing would be one way. What else you could use polynomials for? So like you could practically what will you use polynomials for? Not sure. Like FFT, yeah, but I mean like multiplication. If it's not like FFT multiplication to get the constants, the not the constants, the coefficients of a polynomial, extending. I mean, you don't use really FFT for anything else, right? And polynomials, you don't really use that for anything else as well. Like, I'm not sure. I would think that this hashing idea is pretty much what that is. But also it's like the addition, no? It has the property that it adds something to the number. It makes it bigger. It makes it with more bits, you know. But XOR, on the other hand, it flips it. So it flips bits. It flips dimensional. In some dimensions, it flips the number. So there could be an idea where you would hash that. Is it even like, is it possible maybe to encode more no. You want to encode more information. It would just again hashing like modulo. Because you flip bits. When you find so essentially adding to the same numbers, it actually flips it. So it actually makes it zero. So then the field where the negative number of a number is a number of itself, if it is itself, right? So like if I have a XOR a, it's zero. So a means a is equal to negative a if negative is defined as in that field, right? Technically, right? So so probably like given two arrays, you can hash them like this. Would it be faster to hash them like this? Would it be theoretically faster? Because XOR is faster. But Nim product is not, right? Nim product is slow. Is it theoretically faster to hash strings with the Nim product? We can make a separate video on like this topic. Let's try. See, yeah. Faster to hash strings with Nimber Field. Oh, nice library. Binary index tree, binary dynamic bits and that's really cool. That's really cool. That is a cool library here. That is a cool library. Union find line container range sum add bit range sum range add bit. Okay, that's not hard. Slide window aggregation. Let's see. Sparse table. Sparse table is called. But the sparse bit set, I want to know if he has some like sparse bit set maximum try. Rectangle, arbitrary FPS, blur, what can we see? Multi-point evaluation, yeah, all of that tricks. Entity. Functional low links. Let me just check here. Okay. Minimum cost arborescence. Oh, minimum cost arborescence. Oh, that's kind of nice. Okay, hash maps. Inner math. What is inner math? LC. Okay, link a tree. Multi-point simulated annealing. Okay. Grant the number. I want to see that. Yeah. Name product. Okay, primitive root. Semi-ring linear recursive. Yeah, here I'm more interested in this. So math fast. What is binary GCD? That exists. Subset convolution. Yeah, subset convolution matrix, bit matrix, black box linear algebra. Okay, so now we have a lot. Okay, to go through. Okay, slide window aggregation. That's can I translate that to English? It's a monoid of A The following execute at high speed, inserting elements at the end, remove top element, overall aggregate values. Okay, so alright, I will take a look at this. This seems interesting. Minimum cost arborescence. What's the time complex? I mean, the time complex is probably huge, but whatever. Inner math. Inner math. What is inner math? Okay, so like inverse module GCD. Okay, that's easy. Require. What is this? Log table. So a log table. What is a log table though? Oh, a log table. So like it. Yeah. I see. It calculates logarithms faster. Pre-computations. I don't think you would ever need that, but whatever. What is required by? Required by simulate annealing. Okay, simulate annealing is just never happens. Grande number. Yeah, Grande numbers. I mean, Grande number of what? Of some graph. That's cool. That's cool to have. Cool snippet. Cool snippet to have. Grande number of some graphs. Nimber to whatever that is. Polynomial ring. Okay, yeah. Okay, that makes sense. Okay, Nimber to field. Field to Nimber. I mean, yeah, the nim product here is defined like this. The calculation of the nim product is something similar what we have learned, but this is a much more complex structure here. Semi-ring linear recursive. So semi-ring linear recursive is something linear recursive where you're given what is RIG? It's some value. Okay. So you're given some k term, get coefficients, increment, doubling. I don't know what is this, but semi-ring. Oh, so yeah, yes. It's probably some recursion with modulo, with like semi-rings. I need to see about that. Binary GCD. Binary GCD is what, essentially? I'm not sure. Black box algebra. So cool snippet here that he has sparse matrix. Parse areas. I mean, okay, that we'll never use. So semi-ring remains. This is Nimber. This is Nimber to Poland. Nimber to field. I'm not sure why. I'm not sure why do you need it. Depends on different structures? Oh, no. Then we don't need that. Then we don't need that. Okay, that's cool. Let's go. Mod int. Arbitrary mod int. Arbitrary mod int? Wait, you can't use arbitrary. What is What is the Barrett reduction though? I'm just learning so much stuff from this guy here. Barrett reduction. Why does it here? Why does it here? Probably for division, right? Because if you Barrett reduction, quotient, remainder, so it makes like for the inverse, right? Okay, like the inverse is what? How it is defined? It is defined, but it is defined ordinarily. Where does it use Barrett reduction though? Static Barrett mod set mod. Oh, he's reducing get modulo, and then he's okay. I'm not sure. Oh, Barrett reduction is just he's using for the division, but that's prime mod int or Barrett reduction mod int. Montgomery mod int. So okay, vectorized mod int is that exists as well, like multi-dimensional, or no. This is just something else. Arbitrary multiplicative function device, GCD convolution, famous series, prime counting faster, sum of multiplicative, sum of torsion functions. Famous multiplicative in preparation of the upcoming is any f of n is any GCD a b equals 1 a natural number. This okay, we know what the multiplicative function is, but so famous multiplicative functions. That's what he's saying. All right. So like just like okay, I see. Just some famous multiplicative functions, but in one file. Okay. That's entity and FFT ordered map. Random graphs. Probably planted clicks somewhere. How does he implement the tree? Lazy reversible tree node. That's cool. I mean, you could implement that yourself, but whatever. Dynamic lead shutdown trees. Okay. Segment set functions. Oh, the different convolutions. Yes. Okay, different convolutions. So like. Okay. That's known. Shortest path. String algorithms. Okay, everything is that known. Block cut tree. Now that I'm not sure. I don't know that. I'm not sure. Block cut tree, but okay, Cartesian tree. Okay, that's tree, right? Or maybe it's is that UV of LCA if UV corresponds to the minimum value of and the precomputation is used. Okay, so the selection LR, which AI is smallest vertex. Okay, let's not get you get over with. Let's just see if there's more mathematical things here that concerns us. Something like about game theory. Verify. So there's no game theory here. There is some game theory here. Impartial game solver. So what is the impartial game solver? Can I just copy this? Get translation, detected language, Japanese. Board. Okay, move. Game is a vector. State is of type move. If move is void. Oh, this is just a solver. So like okay. So this is just a template solver, and you're defining a class board and a class move, and you're defining, okay, what's the board and what can you do on this board, and the game solver is just asking your class some things. Partisan game is okay. What is this? Okay, this I don't know. Partisan game. Okay, there's some link here. I'm not sure. So it's a type of a game. It's a type of a game. Okay, this is insane. Okay, this is insane. I mean, yeah. This is a type of a game. All right. So, okay, we took a look at what snippets this guy has. Let's see semi-ring linear recursive. What does solving linear recursive equation with polynomial? This is interesting. I mean, this is interesting. Yeah, hypergeometric sequences, so like there's polynomials as coefficients. It's interesting. I mean, but that is just, he wrote a whole paper on it, so I'm going to take a look more at what he does. Okay, so in max properties in topology, I can't find the problem which was based on some field in topology, but whatever, like just not gonna bother right now. We're already 2 hours in the stream, so it seems that there are no good game theory. One good game theory lesson is from Pavel Martin. He has some like Pavel Mavrin. He has some game theory. if you want to check out these graph games, it basically explains what are the basics in game theory, and I'm not going to do that here. Yeah. So game theory is interesting topic, and this seems kind of interesting, although we have to make a stream which is totally dedicated to game theory, right? I mean, we have to make a stream. Okay, so let's go back and let's see what we can do about this XOR problem and end up the stream here. We can certainly optimize the Gaussian structures, and I think it will pass if we're clever enough how to. But the memory is just so big that I'm afraid that constructing the memory takes much more than querying it. So essentially it's like it takes so much memory, and you have 60 longs, so that's not good actually. That's 60 longs in one node. I mean, should not be that good. And prefixes, no, we can't do prefixes. It should be a sec tree. It's just the segment tree is just it's just the idea could just in one node save only the vectors that you need and then pair them with like the dimensionality. Okay, we can try something like that quickly. We can just save vectors that we need, and then after going all of these vectors, I'm just gonna okay, so let's say that we have something like this. So if I what am I interested in is I'm interested in the first bit that is on. So like you have some vector and all of these are zeros, and this is the first bit, first on bit, right? And I'm interested in this bit. Technically, and if I save all of the vectors in like the constant behind this is very big, you know, and like merging two bit sets maybe should be done quicker. So how do you merge two Gaussian distributed? How do you merge two matrices which are both like linearly independent? You could potentially still won't be that slow as well. Like 60 times 60 is very slow for one node query. It has to be like faster, fast merges and fast checkings as well. Like, how do you check fast enough? I'm not sure how do you get rid of that overhead, you know, that 60 times 60 overhead on each query. Fucking unbelievable. Idiots. Essentially, I don't know. Let's read the tutorial because it's already getting too late. This is talking about this, the Gaussian elimination. Oh, so he is projecting some KI matrix here. Wait. Why log max though? N plus Q log max. Isn't some constant factor? Wait. Like, okay, constant factor, they won't say about constant factor, but what is Ki? Wait, Ki, we know. Wait, Ki, oh, the set of integers between 1 and I such that the span from A to K to AI and AK plus 1. XOR of some element. Linear combination, yeah, that's what we said, linear combination. There exists K such that X is in this set from K to Ri minus 1. So there exists some K, so, and the maximum value of such K is greater than or equal than L. Oh, so you want to okay, how it changes a set of integers. So it is prefixing. Probably, yeah, it is prefixing. Consider the unique representation of if AI plus 1 is not in the span, we can compute as this. Okay. What about the user editorial? By using the data structure above, consider linear basis. Since there are n layers in the segment tree and vertices, we can process it for linear basis, merging them in off one. Wait, yeah, it's off one, but the constant factor is too big. Now imagine that your vertex L construct a linear basis in the middle. After that, every vertex has two linear bases on the left and the right. By doing this, since it's much slower than the standard method, it's sure that simply coding can delete it to many TLEs. Here are 3 tips to speed up your code. When constructing linear based on each vector, take down something like insert instead of copying the linear basis many times. So he wants to have one basis, and you don't copy many times, you just add that to the basis. Use fast, and you can get AC since there are. Does that make it that faster? Like, okay. Let's try to improve this. Okay, let's try to optimize it, because I'm sure that this can work. Okay, so instead of having like one base, I'm going to do like, okay, I'm going to have like a base here, Tomopo base or something like that. And then when I'm gonna build it, it doesn't matter, it's building very fast. Yeah, here I will just say, okay, I will get a vector, and then in this base I will say insert a value that insert this vector. This now is a vector of LL, which I can just quickly see in, right? And okay. Now, yeah. I will ask about the value, but the value will be put into this temporary. So like tree.basis dot resize, whatever, like dot clear. Here I will make like this, and now here I can make a function. For now, clearing this base, we'll just say basis dot resize log, and then we'll say like we'll say 0, right? And now this log here factor, I will just put it outside the base, because why do we need to or just make it static? This as well works, right? All right, now this is cool. And now instead of merging, I will have like, okay, like this is fine, but instead of merging, I will have like, when I ask, I won't have like merge of these. I will have like, I won't return a node here. I will return void, and here I have this. Okay, return, and now here, if I have this, I have this index, right? So I need to say Tomopo base dot merge this, and now a merge function will just do a bit, okay, base, no, and then you will just go through the base and you say like insert this vector. Okay, now this merges this function. And now when you're gonna wanna ask, you just wanna ask like this. Okay, this is gonna be faster, but it's not gonna be that much faster. Okay, so okay, I want to clear, and now I want to ask this, and then I can do like I can do the temporary base can x. Technically it should be faster, but now it gives me wrong answer. Okay, so let's take a look at what we've done. We've cleared this and we've asked on the tree. So each ask on the tree will be a merge if that interval is exactly flips. If that interval is exactly, so there's log n times this merge happens. Also, when you merge this, all right. Oh, I need to clear that, right? Okay, but it's still too slow. It's like too much memory. Okay, let's try to copy this pragma thing here. Whatever does that mean, optimization. Is not a string. What? Do you need like that? Optimize is not a string or number. Oh, yeah, it's different types of this. Okay. But it still takes a lot of time to generate the tree. But this is the constraints of the problem, right? So I can't make it times 5, right? 5, okay, 4 times 10 to the 5th, but because of the log factor you need more. But even though this memory is not, then you have a lot of queries. That's the problem. That's the problem. What if you have like log 60? That will work as well. Yeah, but like you don't gain anything here. Okay, so what was the other? Oh, to generate the matrices, we are copying them. So technically it's slow generating the tree, right? So okay, let's see how fast it is. Okay, let's generate an example. Okay, let's see, equal to generator. Okay, let's say you have some random, so let's say you have this many, and then you have just 0 queries. All right, so, and you pick like some number from like whatever. Like and the numbers are too huge. That's why the read is slow. It's so bad. Okay, so let's just generate that. Okay. Let's go stress test. But it's no, I don't want to stress test. I want just to say this in, and then I want to say this, and add like auto optimizations, and then okay, that was fast reading all of these. That was very fast. But what if like I have here 2 to the power of like 60 or 59 minus 1, so like that should be the worst case scenario in generating an input. But that's fast as well. Like the sec tree is so fast. Okay, let's go. Let's say four. Wait, 1.2 seconds. All right. Now let's generate some queries. So let's now generate like. Okay, let's start with 1,000 queries, right? And let's say that, oh, wait, we build the tree and then we do this. Okay, so it still works. Okay, still works. So let's ask for some queries. So for range n, let's L generate to be a random int from from 1 to n, R to be a random from 1 to n. If L is bigger than R, L, swap them. Let's generate some X to be a random. Oh, not a random in here. I wanted to try first at exactly these integers. And this is what I want to try first. Quite fast. Okay. No. Okay, let's now jump in and say have this many queries. Come on, the factory is just too big. 10 seconds. No, we have to optimize it 3 times, at least 3 times faster. Okay, let's see what we can do. Okay, so the building of the sec tree is fine, it's fast enough, it's 1 second, but the answering of the queries has to be as well 1 second. So how is the build of the tree actually that much faster than the sec tree? Wait, I don't have syncing with sync. What if I do this? Is it gonna be faster? Or is it just gonna... What if I do scan Fs here instead of this? And instead of like doing this, I can just do this. So let's just segmentation fault. Oh. It's gonna be... No way, no, I don't believe this. I don't believe this. Yeah, it's wrong. Yeah, okay. Something is wrong here. That's why it's answering this quickly. Yeah. I mean, we got fast the results by scanf, right? But I still don't think that. We still have to optimize the. Let's see. I don't know, 9 seconds. We still have to optimize, even though we use this, it's just too slow. It's like how we merge that, it's too slow, like, okay, what we need to do is like merge it after some x, some y, so we know that like we know this, and now should be theoretically faster. Yeah, this should be theoretically fast. But still 7 seconds on my machine. Which got quite fast as well. How do we optimize it further? Instead of saving all of these, can we we can we're doing it in reverse, so the bits which are the number, if the number is higher, then the bits are more than the so technically it won't matter that much. Like, I don't know how the guy optimized it so well. Like, even that he uses cat tree, like he uses 2 and 1 in the like in he uses some kind of middle node. Probably to get away with this, what this cat tree is probably like, it's about like, instead of binary segment tree, it's about like ternary segment tree or something like that. And that's why it gets away with like higher, like larger intervals are calculated. There are less merges, essentially. There are less merges. But also what you can do is, like, you can have a tree, right? A tree will be the same idea, like, because a tree in theoretically is logarithm, but like logarithm base 2, but you will have like I don't know. Probably there is a way to optimize this even further. It's like I need 2 times more faster optimization. That means like, yeah, probably we can instead of keeping the whole basis, we can make it dynamic probably. But I'm not sure how to make it dynamic, because if instead of vector we store it as, does vector has like some overhead? Can you just do like, a memset function? Is that gonna be faster? No, no way it's that faster, right? Still like 6 seconds. But is it that faster? Probably, yeah. It doesn't have to create these structures. I know what can we optimize further. Now when it's not dynamic, you can't just skip. You have to go through the bases. But you could probably optimize something in the way the sec tree works. Six seconds is too much. It's now we need twice as more, like twice as faster to if it is 18, it won't work, right? Yeah, segmentation fault. It's not enough memory. The segment tree is quite fast, but the merging is not. It's still 60 times 60. So if you want to improve this, how would you improve this? I'm not sure. I'm not sure how would you improve this. Would you improve the merging of two bitwise Gaussian matrices? Because still you don't know what the vector linearity, or you know what the vector linearity is, right? You know, probably. Okay. Okay. So you go through each of these vectors, and now how do you add them fast to the current? So let's just switch to the other screen. Let's just switch here. So our bitwise thing here. Well, let's just. How does it load down? Let me get this bitwise thing here. Let me add another thing, bitwise CPP. Let me just here. Let me do it like this. Let's add this, and let's see that. Okay. I will do this. I will pick some array And then I will print the vectors in this basis. So what I'm doing is I'm saying, okay, I'm doing this. Now let's pick some numbers. Let's pick 1, let's pick 5, 1, 7, 8, and 3, or whatever. Like, okay, like most of them are gonna be 0, so like I just need from like whatever, like 7 digits. I don't need more. So essentially all of these down here will be like in this form, 0, 1, 0, 0, 1, 0, 0, 1, because this will be cleared. This will clear this. But the first vector won't be. So technically this is a lot of vectors, so let's just do a little bit less. No, 7 is just 7 to, okay, whatever. Oh yeah, so here we see that the independence is different. I don't know. Wait, we can break if we can break, right? No, technically, no, the ith bit doesn't need to be set, but if there are bits set downstairs, then we can't just break. No. So I don't know how this guy optimized it. Really, like, I'm not sure how he optimized it, but apparently, okay, this function is called once per query, so it's fine. Apparently this merge is too slow. Like, this merge is quadratic, right? Apparently you can do it faster. Let's just submit it once again to see how like does it pass. Maybe I get wrong answer with this merge, because I'm not sure if I can merge like this because of the component wise the structure of the Gaussian matrix. I don't think I can merge it like this, but let's try it. Like, let's try it. I don't know. Oh, it's taking too long. I just want to see. Are the tests public though? I know that you are not seeing my screen. I'm just trying to see. AtCoder test cases. I want to see how fast does it run on my computer. I want to see, like, is it correct? So I can switch to this screen actually just to see. Okay, these are the tests. The task is 223, so 223 AtCoder 223 ABC H. Download that. Doesn't matter, just download it. No, wrong. Okay. I just want to say this. H. Oh, still not downloaded. Whoa, that's a lot of megabytes of tests. Whoa, they're strict. Where was the submission though? So not two wrong answers. It could be not actually not trying to merge like that. Theoretically not fine. Probably what I'm doing is not fine. Oh, the index value insert vector L. I mean, we'll try now to debug this a little bit. So let's see H. Extract here. I'm not sure what. In, what is in? Oh, because it's a file, it doesn't let me. Okay, in and out. Yeah, nice. Okay, here's what we're gonna do. Let's switch to this screen. Okay, here's what we're gonna do. We're going to okay, let's first see if everything works. Oh, Python generator.py in one. Segmentation fault for what now? Oh, maybe I need to rebuild it. Okay, now this works. Okay. Okay. Now I want to see their test cases. So I want to say, okay, in test case 000 out, let's say 00. Okay. It's just the constant factor, but I want to be sure that, okay. Now the difference between alt 0, 0 and alt, okay, let's just see how does alt 0, 0 look in the error. So it says no, okay. Let's see the difference between alt 0, 0 and alt add test 00.txt. Let's just cat that as well. I mean not cat, code alt test 00. Oh, it's totally different. These are all yes, yes, and these are all no's. Let's just code in test 1100. So I have some huge numbers here and a lot of queries. A lot of queries. All right. So why does it fail? If I change, instead of doing this build, I want to see if actually the build fails. Let's return this to, instead of building, I'll just do this in tree that put I, now the node, no, I'll put if I here, and now here this way, this insert vector this. Okay. Let's again build this and let's see if that's work. If that works again. No, still no. So what could it be wrong? Should I go from log to the start? that's fine, that's fine, that's fine. Not sure what's wrong. Okay, it doesn't really matter now, it's too late. Is can wrong? If it's anywhere no, so if it is not oh, could the log be insufficient? Could that be true? Could the log be insufficient? No. So if it is 0, so if it is not x, if it is 0, no, so you put it. But no, so you want to, so you do this, and then when you on the end you do this, isn't it? Like I'm not sure. Like it should work, but was that the bug all day long? This is even slower due to the yeah, now this is correct, but I mean come on, now it's way too slow, like way too slow. That's because you have to compare a lot of things. I'm not sure how he did it. So like, let's see the difference here between these two. So what is the difference down here? They're all yes, no? Yeah. I mean, it's way too slow to merge it in a segment tree. It's way too slow. If it was to 32 bits, maybe it will pass. But 60 times 60, it's probably way too slow. What if I'm interested if I do this? I'm interested if I do that. So like if I compile this and run it. Yeah, it's way too slow. Like you need it 10 times more faster, 10 times faster. And if out 0, 0, 1 without 0, 0. Yeah, there's no difference. Is the operator that much that slow? I mean, it shouldn't be, you know. I don't know why they put so many queries though. Yeah, it's too slow. It's so slow to merge, but whatever. It's correct. It's still correct. It's slow, but it's correct, right? I mean, oh, we can try building it with like the build procedure, no? Let's try if we're building. Let's try. Yeah, that's correct as well, but it's too slow. It's again the build procedure. It's once and it's fine, but with having these lock-in times 60 merges per query makes the constant factor just jump. It just jump way high. And now the idea is here even that like, okay, we merge them. We can't just, if it is, can we just break? Like I'm really interested if like I can just break. No, I can't, right? Yeah. Yeah, I can have a 0 vector. Yeah, I can't break. Okay, that's gonna be it for today. We tried couple things. We learned couple of things. I mean, that is what it is. We couldn't optimize this problem. Probably let's just for sakes look at the standings. Let's see if someone did our thing with, like, let's say this guy probably had TLEs, right? Oh, wrong answers. What did he use? I'm wondering. He inserts bases and for he sorts the queries in such a way that like I mean, all right. Okay, 61, okay, that works. What about... So he sorts the queries and he's using that trick of going to the right and then like seeing that the linear bases won't get like you're essentially the linear bases will get filled and then like for the answers for all, something like that. I mean, okay. So, but it's interesting, like interesting segment tree of these bitwise Gaussian eliminations is interesting. So we were correct. It just needs optimizations. Okay, thank you so much for watching, and I'll see you next time.